Which of the following chiral molecules have the S configuration? So when we are assigning R and S, there's a few steps that we need to take. After we identify that chiral carbon, the first thing we want to do is we want to assign priority to all of the groups. So we have 4 things attached to a chiral carbon atom, so we're going to have priorities 1 through 4. And we assign that priority by atomic number. So we're looking for the highest atomic number. And the key there is that you have to go atom by atom and compare. So you look first at the atoms that are directly attached to that chiral carbon, and then if you need to, you say, well, what are those atoms attached to? Okay, so you assign the priority to those groups. And then what you're going to do is you're going to orient the molecule so the lowest priority group is facing away. So it's facing away from you. So what that means, if you're looking at a 3-dimensional structure with dashes and wedges, that means you're looking for it to be on that dash bond, okay? And then after you do that, you're gonna draw an arc from groups 1, 2, 3. So that's what you'd be seeing if you had the 4th one pointing directly away from you and be kind of eclipsed behind that carbon. And you're gonna draw an arc from 1 to 2 to 3, and if it's going clockwise, like this example, then that would be an R stereocenter. And if it's going counterclockwise instead, so 1 to 2 to 3 going counterclockwise, then that would be S. So this is what we're looking for. We're looking for that counterclockwise rotation of our groups, as long as we have that lowest priority group facing away from us. So we've got here examples of 3 different types of molecules. And so I want to start with the second one first. And the reason why I'm starting there is because this is actually the easiest example of these 3 for determining the chirality. And the reason why I say it's the easiest is because the way it's drawn right now, the lowest priority group is already facing away. So how do I know that? So here's our chiral carbon. We've got 2 bonds that are in the plane, and we see the bromine is coming out of the plane. Now this is a tetrahedral carbon, much like 1, so we need to have a bond that's going into the plane. And so it's not shown, so that means it's implied to be hydrogen. So that means we have a hydrogen that's facing away from us. And since we assign priority by atomic number, and hydrogen has the atomic number 1, so there's nothing below it, that's always going to be priority 4 when you see it. So in this case, this is our best case scenario because our priority 4 is already facing away. So that means all we have to do to decide this is assign our priorities and draw an arc. We don't have to try to redraw or reorient this molecule in any sort of way. So from that chiral carbon, we see we have a bond to a bromine, so that's going to be our highest priority. And on this side, we have a bond to a carbon, and here we have a bond to a carbon. So since they have the same atomic number, then we need to consider what they are bound to. So if I look at this carbon, carbon always has 4 bonds. I've got 1 bond to carbon, 3 bonds to hydrogen. Okay, and if I look at the next carbon atom, I have 1, 2, 3 bonds to carbon, and then a bond to hydrogen. And so I've listed these in decreasing atomic numbers so I can directly compare and see where I hit a point of difference. So carbon, carbon, hydrogen, carbon. So this side is going to take priority. So that means that this is priority 2, and that methyl group is priority 3. So now when I draw this arc, 1 to 2 to 3, and my lowest priority group is facing away. So I see that this is counterclockwise, so this is an S stereocenter. So I have found 1 of these chiral molecules so far to have that S configuration. All right, so the next one I'm gonna look at is 3. And that's because this is like the easiest type of problem. This is the next easiest type of problem. And the reason is where the hydrogen is. And hydrogen's not always going to be your lowest priority group. You might have a chiral carbon that doesn't have any hydrogens at all, but if it does have one, that's definitely your lowest priority. So here's our chiral carbon. And in a Fisher projection, so this is a Fisher projection. So in this sort of projection, the horizontal bonds are understood to be sticking out of the plane. And the vertical bonds are understood to be going back. And so what this means is that your lowest priority group is exactly opposite of where you want it to be. So it means when you draw your arc, whatever direction it looks like it's going, if you were able to kind of mentally get behind it, you would actually see it going the opposite way. So that gives us a trick to be able to assign the stereochemistry without having to redraw the molecule or build a model or anything like that. So we see priority 4 is always the hydrogen, if you have one. So the next thing we have is a bond to carbon, a bond to oxygen, and a bond to carbon. So oxygen of those has the highest atomic number. And then we have a carbon and a carbon. So those have the same atomic number. So now we need to consider what those carbons are bound to. So this top carbon has a bond to the center carbon and 3 hydrogens. Okay, and this bottom carbon has a bond to carbon, 2 hydrogens, and an oxygen. So if I list those in decreasing atomic number, I'm going to put the oxygen first, then the carbon, and then the 2 hydrogens. And that just allows me to really quickly see the difference. So I can compare carbon, oxygen. Oxygen is heavier, so that means this bottom group has priority. And then the top would be 3. So with your lowest priority group sticking out at you, your chirality center will be opposite what it looks like. Right, and that's because if we think about it, we want that oriented away from us, so it's kind of like we're standing behind and looking at it from the wrong direction. So standing this way, I look and I see that these are going clockwise. Okay, so this looks like R, but if we invert it, we get S. Okay, and so we're not actually like switching groups or anything like that. We're just recognizing that if I stand on this side, it's going to look clockwise. But if I was standing behind the molecule, I would see it as counterclockwise. And that's the orientation that it's supposed to be in by definition in order to assign the chirality. So we've got another one that is S. So 1 and 2 so far are S. So easiest, you can directly read it. Second easiest, it's the opposite of what it looks like. So you assign it and then mentally say, okay, it looks like R, but it's actually S. This first one is where we're going to have to really pull out all of our tricks because our hydrogen is not facing out or facing back, it's in the plane. Right? And again, remember hydrogen is not always going to be your lowest priority group. If it's there, it is, but you can easily have a chiral center that doesn't have any hydrogen. Okay? All right, so let's assign priorities to these remaining groups that we can see. So hydrogen is the lowest priority. So we can see priority 1 should be the sulfur, and then we've got 2 carbon atoms. So they both have the same atomic number. You'd want to consider what those carbons are bound to. So this carbon has a bond to carbon and 3 hydrogens. And this carbon has a bond to carbon, carbon, and 2 hydrogens. So the carbon, carbon, that's the same, carbon, hydrogen. There's our point of difference. So that means that this top group has priority, and then this is priority number 3. Now, where you go from here to solve it, there's quite a few tricks. I'm going to show you the most foolproof one. If you're able to, you really want to be looking at it from this angle. So you might be able to imagine that you're looking here and you're going to see this clockwise rotation. But if you want it to be foolproof, you want to make sure that you redraw the molecule with that priority 4 in the back. So I'm actually going to give the hydrogen the priority 4 number this time. So we're going to use a trick. Whenever you switch 2 groups on a chiral center, it switches the chirality. So if you switch 2 groups, that inverts the chirality. Right? So if I switched 4 and 3 to get 4 where I want it to be, I could assign the chirality from that, but I'd have to keep in mind that I've switched 2 groups, I've inverted it, so I'd be doing the same sort of thing as here. Here's a more foolproof way of doing it. So if I switch these 2 and I also switch these 2, what I redraw is going to be the same as what I started with. Okay? So let's repeat that one more time. If I switch these 2, I would change the chiral center. If I switch these 2, I would change it back, right? As long as I did those 2 switches. And so the first thing that you're switching, there's no rule about what number except for the fact that you want 4 to be on a dash line. So the first switch you're going to make is your priority 4 with whatever is on that dash line, regardless of what number it is. That's just where you want your priority 4. So if you switch those two, you should also switch these two. And that's to make sure that you're redrawing the same chiral center. And when you do this, if you're just interested in RNS, you don't actually have to redraw the whole molecule. You can just put in the numbers. So we put 4 over here. We put 3 over here. We switched 1 and 2. And so this represents the same molecule that we started with. So now we can draw our arc from 1 to 2 to 3, and we see that it's clockwise. So this center is R. So we were looking for which centers have the S configuration. So that is 2 and 3.